In this video, I'm going to talk about altimeters, which are one of the most useful tools when navigating in mountainous areas. Of course, GPS exists, but there are some limitations and downsides to GPS, which we'll talk about. But first, what is GPS? So GPS stands for Global Positioning System. That's 24 satellites that orbit the Earth and broadcast a signal about where these satellites are and what time it is. Devices on the ground then receive these signals from at least 3 satellites to determine where you are on the globe. Now, we talked about radios and signals in a different video, which I'll link. GPS is the US's version, which is run by the Space Force, but the EU operates Galileo, Russia operates GLONASS, and China operates BeiDou. It's important to remember that GPS devices are only receiving and interpreting signal from these satellites. That's actually why your phone works in airplane mode, because it's not giving off any signals to figure out where it is. It's receiving the signals and then doing some calculations. Now, GPS has become part of our everyday lives, but there are some weaknesses. The first one is called GPS shadow. So on flat ground, typically between 5 and 10 satellites can be visible at any time, but terrain can block low and medium elevation satellites in the horizon. In urban environments, GPS can be augmented with Wi-Fi signals, but that doesn't exist in the mountains. So the next weakness is GPS jamming. So GPS satellites are about 12,000 miles above the Earth, and their signals can easily be overpowered by ground-based emitters. These emitters can transmit frequencies similar to GPS frequencies to make it difficult for a receiver to understand where it is. This jamming is commonly seen in the recent Russia-Ukraine conflict due to the use of GPS-guided munitions and drones. Another weakness of GPS is spoofing. Spoofing makes the receiver think that it's in a different position than it actually is in by transmitting either false data for positioning or false timing. Now, this is considered elaborate and deliberate because of all the work that has to go into achieving this. And you can see in 2024 on the right, the daily estimated number of flights, that's commercial flights, affected by GPS spoofing. You can see Middle East, Black Sea, Russia, Korea, and India, Pakistan border. So you can see up to 2,000 flights a day affected by GPS spoofing. So this is a screenshot from gpsjam.org. Notice the significant jamming in the Middle East, the Baltics, Eastern Mediterranean, and the Caucasus. Basically, places where there's armed conflict right now, there's a significant amount of reported GPS jamming. So what's the solution to this? The solution, at least for the military, is something called the DAGR, the Defense Advanced GPS Receiver. Basically, all of our GPS satellites emit an encrypted signal called M code that can be received by our military GPS receivers. This code can make it harder to jam or spoof military GPS signals, and it even lets the user know if it detects any spoofing or jamming. You can see that top picture, that's a Garmin Fortrex, which was commonly issued to troops. They don't receive any encrypted GPS signals, so they are vulnerable to jamming and spoofing. The bottom picture, that is a dagger, and you can see it is basically the size of a cell phone, a little bit bigger, a little bit heavier, and that's what dismounted troops and even in trucks are expected to carry in order to not be jammed or spoofed when using GPS signal. So what's another solution to this? Ultimately, we can learn how to fight offline. The innovation adaptation cycle can lead to technologies basically canceling each other out and causing the need to revert back to basic skills. All right, we want to use the resources that we have to give us the biggest advantage possible. We can learn to fight offline and practice fighting offline using methods that require little to no electrical power or outside resources. A note on the electrical power, the Garmin Instinct, which is a common watch that's worn in the military that has both GPS and altimeter, that can last about 2 days while operating in GPS mode. Those Garmin Fortrex from the previous slide last about a day or two on 2 AAA batteries. Daggers last, like I said, a few days unless they're plugged into a truck. Meanwhile, that same Garmin Instinct watch can have the altimeter running in the background, so in theory it can measure your altitude for about a month. In places where you're worried about power management, an altimeter can be another great tool to have in addition to GPS to help you understand where you are. So what is a barometer/altimeter? Gravity is strongest when it's closest to the center of mass. Flat earthers are not going to like my videos. So Earth's gravity pulls air towards the center, so squeezing air tighter the closer it gets to the Earth's surface. This causes a change in air density with a change in elevation. Based on this air density, we can determine our altitude. This is also why there's less oxygen available at higher altitudes than at lower altitudes, just because it's less dense. Now, air density and pressure can change slightly with temperature and humidity, but generally it's the same all around the world at the same altitude. So the air density at the beach in Hawaii is going to be similar to the air density at the beach in Madagascar, for example. For this reason, it'd be impossible to change the air pressure in one specific location to alter navigation. Basically, it's jam and spoof proof. This info is only really helpful for navigating environments where there are changes in elevation, such as mountains and hills. Knowing your altitude won't tell you exactly where your location is like a GPS, but it can give you another data point to help you navigate, and I'll give you some examples. So just to recap, elevation data is measured using sensors on aircraft, and that's put on a two-dimensional topographic map. And typically, elevation change is shown using contour lines. Now, yes, this does require some outside effort besides your own, unless you're flying your own plane, but all this data is already captured basically all around the world. So finding your location on a map. There's two main ways you learn how to find your location on a map in like Land Navigation 101. And the first one is resection, and the next one is modified resection. So with a classic resection, you measure your heading towards two different points. You follow those lines back to yourself, and you basically triangulate your position. With a modified resection, you can have your heading towards one known point, and then you are physically along a linear feature, and where those two intersect, that will give you your location. The other way you can do this is just being on two linear features. So let's do an example of a resection. On this slide, you can see we have two known features. We see that peak on the left, labeled number 1, that's North Howe Peak. And then on the right, we see a cluster of lakes, and I will pick the most defined feature. For me, that is the right side of the closest lake. So I take out my compass, and I see what magnetic heading it shows towards North Howe Peak, which it would be in this scenario, 329 degrees magnetic. Then I turn to the right, and I measure the heading to the right side of that lake, and that is 27 degrees magnetic. So now we're going to have to do some math, because remember, the north that we get from a compass is not going to be the same north that we see on a map. So the compass is going to give us our heading in relation to magnetic north, but for the map, we're going to need it in relation to grid north. And the way we do that is we subtract the difference between grid north and magnetic north for that area. In this area in Maine, that angle is 15 degrees to the west, so we're going to have to minus 15 degrees for the GM angle. So for our first known point, we have 329 degrees magnetic minus 15 degrees of that GM angle, and that gives us 314 degrees grid to that first known point. For the second known point, we have 27 degrees magnetic minus 15 degrees, and that's going to give us 12 degrees grid to that second known point. Now we're not done with the math, because we need the back azimuth. So we're going to take our 314 degrees to the first known point minus 180 degrees. That's going to give us 134 degrees. So I start at that peak, and I draw a line going back 134 degrees, and that's our first line. That second line, we have 12 degrees grid. So from our second known point, 12 degrees grid, we have to get the back azimuth of that, so that's plus 180. That'll give us 192 degrees of a back azimuth. We see where our first known and our second known intersect. You can see our current location is along that trail. But if we already know that we're on that path, then we can do a modified resection and do basically half the math and only find the back azimuth from one of those points. Now, the only thing better than less math is no math at all. So in this scenario, I know I'm on that trail, and I look at my altimeter, and it tells me I'm at 4,000 feet. I look at the map, I see where that trail reaches 4,000 feet. You can see the 4,000 feet contour line, and that will give me my exact location where those two intersect. Now you might be thinking to yourself, I'm not always going to be on a trail. And that's true. So on this map, I took the trails off, but I might still be on that identifiable feature, such as a spur. And I check my altimeter, 4,000 meters. So I'm on the spur, 4,000 meters. That will give me my location. Let's talk about profile views for a second. So profile views are used to show elevation gain and loss along a certain route. Now this can be done by hand or using a mapping software. You can see on the top, that's taken right from the US Army Land Nav manual, and you can see someone is sketching out that profile view by hand. At the bottom, that's using a website called Calitapo, and you can make routes, and it will show you the profile view of that route. But this can be useful to visualize your route in terms of elevation instead of distance, which sometimes that can be a little bit more useful. And why is this helpful? Well, this is helpful for route planning and group management. So you can plan breaks based on altitude gain. You can also determine how close you are to your next checkpoint. This can be especially helpful at night when you can't see the terrain to train associate or perform a resection because you can't see very far. So in this scenario, my group and I want to go from the SP start point on the right side, that's at 1,500 feet, and we want to get to the saddle at 4,300 feet. Well, we know that we have a good break point at the pond at 2,900 feet. That pond is going to be hard to miss, and I know the elevation, and you can see it's going to take us about 3 miles to get there, and then that last mile is going to be short but steep. So I know that pond might be a good break point to, when we get there, maybe we can get something to eat, get something to drink. If we need to refill our water, maybe we can do some water purification at that pond. But I know that the elevation of that pond isn't really going to change. So that's a good point along the route to make a checkpoint. So we leave from the start point and we start gaining elevation. I should be able to watch my altimeter go from 1,500 feet all the way up to 2,900 feet. And when I get to the lake, it should say 2,900 feet. And now I know my exact location on the map. But what if I get to the lake and it doesn't say 2,900 feet? Maybe it says 3,100 feet. Well, this could be confusing, but there are some reasons for this. So what affects air density? So barometers are affected by both temperature and humidity. Okay, so for temperature, colder air is more dense, and that would make a higher pressure, which would make you seem like you're at a lower altitude. The other side of that is warmer air is less dense, and that will be a lower air pressure as if you're at a higher altitude. So in this scenario, say we started moving in the morning when it was cooler out, and then it warms up throughout the day. Well, maybe I set my altimeter at the start point when it was 45 degrees, and now in the middle of the day, it's 75 degrees. It's going to tell me that I'm at a higher altitude than I'm actually in. The other thing to think about is where you have your altimeter. Most people wear them, like myself, on as a watch. The temperature under your jacket sleeve can change. As I move and sweat and get warm, that temperature under my sleeve might increase, and then that might give me a higher altitude reading than what I'm actually at. And that other thing that can have a big effect on barometers is humidity. Dry air is more dense, and that'll give you a higher air pressure, which will then give you a lower than normal altitude reading. Opposite is true with moist air. That's less dense, that'll give you a lower air pressure and a higher altitude reading. So in the scenario where the altimeter is underneath my sleeve, as I start to move and sweat, it's going to get more moist under there, and it's going to give me a false higher altitude reading. And now the final thing that can really affect these barometers is changes in weather. So low pressure systems, which are usually accompanied by precipitation, whether it's snow or rain, that's going to tell you that you're at a higher altitude than you actually are. So if you're staying in one place and you see that your altimeter is telling you that you're going higher and higher and higher, That's probably because there's a low pressure system coming in, and if it's not already raining, it's probably about to rain. And the way I used to remember it is if I'm showing that I'm at a lower altitude is high pressure. Well, what's at low altitude? The beach. So if it's good weather, I'm going to the beach. If it's showing me that I'm at a higher altitude, that means that I'm in for a storm. I'm going to be on a mountaintop in a storm versus nice weather at the beach. So my point is that these things can affect our altimeter. So when we're at a known point, like at this lake, we can change our altimeter and calibrate it to say exactly where we actually are. So if we get to this pond and it doesn't say 2,900 feet, I'm going to change my altimeter to make it say 2,900 feet. So let's continue on our journey. We continue this path and we're climbing and we are almost at the saddle, or we think we're almost at the saddle. We can check our altimeter on our way up. If it says that I'm at 3,150 feet, I can go to the map and I see if I'm at 3,150 feet, that means I am almost at the saddle. I might not be exactly along my path, but I know where I am on that contour line. So I know that I'm almost at that saddle. And then finally, when we do get to that saddle, that is, again, a known point where I know the altitude. So I'm going to reset my altimeter to reflect where I actually am. Okay, so here's a completely different example of me skiing down a ski slope at night. I know I need to make a right-hand turn at 1,872 feet, but I can't really associate, and I can't really see all these trails at night very well. They all look the same. I'm wearing a headlamp, so I can only see maybe 20, 30 feet in front of me. But even if this was a tactical environment and I was wearing night vision, again, I mean, you can see a little bit with night vision, but it's not going to be enough to where you can terrain associate very well. But you can see as I'm skiing down, I can look down at my altimeter, and right there you can see I look down and it's 1,938 feet, and that lets me know that my right-hand turn is coming up soon. So keep my eyes out on the right side of the slope, and it's just a visual cue, almost like a countdown, to where I know that my right-hand turn is coming up, because I don't want to miss that right-hand turn and then have to put my skins on and go back uphill. Okay, so to summarize all this, the case for altimeters is they are jam and spoof proof, they require less power than a GPS, and they're just good, quick references. The last thing that we didn't talk about here is medically there's only a certain amount of elevation that you should gain in one day, and altimeters are a quick, easy way to tell how far you have moved in that day and how far you can move for the rest of that day. On the right, there's a picture of me in the Caucasus Mountains, and you can see that's the hand that I photoshopped into all those other pictures. But this is a good example of knowing that I was at the absolute limit of how far I should move up in elevation that day, and then we actually ended up turning around and then losing some elevation. But that's a bigger topic that I would like to talk about at some point. Now, you don't have to go out and buy an altimeter just to get started on training with them. Most newer phones have built-in barometers, and if you go to the Compass app on an iPhone, it'll actually give you your current altitude based on that phone's barometer. And that's enough to get you started understanding altitudes along your routes. If you use an altimeter on movements, let me know what you've used and how you used it. If you know someone who this information would be useful to, please share it and put any questions and comments you have down below. Thanks.